Okay, we're going to talk about single replacement reactions. Now, a single replacement reaction, or sometimes called a single displacement reaction, is a reaction where you have some free element that displaces another element within a compound, meaning that then you form a new compound and you have a new free element. Okay, and so that's the basic idea of the reaction, is you have something essentially by itself, and then something that's got two things bonded together, and the thing by itself kind of kicks one thing out of that compound and replaces it. Okay, and so that is a single displacement or single replacement reaction. So when this occurs, it can occur with kind of different types of things. So one basic type of single replacement reaction is when you have some metal that replaces a metal within an ionic compound. Okay, so this is going to happen when you have some metal reacting with an ionic compound. Okay, so I've got an example here of aluminum reacting with iron 3 oxide. So aluminum's a metal, and iron 3 oxide is an ionic compound. And so what happens is that metal replaces the metal in the ionic compound. And so what you see is the aluminum ends up swapping places with that iron. Okay, so in the product, you have aluminum with the oxygen, and you have iron by itself. Okay, and so the like element replaces one another. So the metal replaces the metal. So I have a new compound formed, and I have a new free element in this reaction. Now you do have to be a little bit careful here. When the metal replaces the other one, you have to figure out the formula of the compound, think about the charges. Okay, so in this case, you would think about when aluminum forms an ion, what charge does it form? And it forms an Al3 plus. And so then when it combines with oxygen, it's combining with O2 minus. And so that's where the Al2O3 comes from. The 2 subscript is not carrying over just because there's a 2 on the ion. Okay, and so that ratio won't always be the same. In this case, it happens to be because the iron is iron 3 ion and the aluminum forms a 3 plus. Okay, but to predict that compound that's formed, you not only need to, swap the metal with the metal, but you need to put it in the correct ratio to balance the charges. Okay, so we'll look at some examples of those, but before we get to that, let's talk about the other possibilities. You can also have a non-metal replacing the non-metal in an ionic compound. So instead of reacting metal with an ionic compound, we're reacting non-metal with an ionic compound. So in this case, chlorine is a non-metal and bromine is the non-metal in the ionic compound. So those things are going to switch. Okay. And so what we get is then potassium bonded to chlorine instead of bromine, and then bromine coming off by itself. And again, that product that forms is going to be based on the ions. So chlorine, when it's an ion, is Cl minus, and potassium as an ion is K plus. So that's why it forms KCl, which happens to be the same ratio as when it's with bromine, but that doesn't necessarily have to be the case depending on what non-metal it's reacting with, and what metal is there. And then the element that comes off on its own, remember, always becomes neutral. So that was the same as above. The iron that was freed from the ionic compound then becomes neutral. Same with the bromine. When it comes off, it's not Br minus anymore. It's Br2 because that's how that compound exists by itself. And so those probably are two of the most common things that we deal with single replacement reactions. You either have a metal replace a metal in an ionic compound, or a non-metal replace a non-metal in an ionic compound. Those are the most common type, but we can also have single replacement reactions occur with metals reacting with either water or acid. Okay, and what happens there is the metal replaces the thing that is behaving like a metal, which would be the hydrogen. Okay, so when you have a water molecule, it can be helpful to think of it as it being really made up of H plus and OH minus. Okay, and that should help you then realize, well, if I'm reacting it with a metal, so strontium's a metal, strontium will form an Sr2 plus, so a cation. That's going to want to swap out for the cation in the compound. And so the strontium kicks out the hydrogen and replaces it. And so the hydrogen, when it gets kicked out, becomes hydrogen gas because it becomes neutral. But the strontium then combines with the OH minus, and so now that makes a new compound, the strontium hydroxide. Sorry, my notes are probably getting a little out of hand on here. I'll erase some of these ones above so we can focus on the reaction we're looking at. Okay, so if you think about the water as being H plus and OH minus, and you think about strontium when it becomes an ion, so when it wants to become part of a compound, it's going to become an ion. And so what's going to happen is that strontium binds to hydroxide. So if we take these two and put them together, you're going to need two of the hydroxides. So that's where that formula comes from. And then hydrogen by itself becomes neutral. So that's one thing. You could have any metal react with water, and the reaction, if it occurs, is going to form a hydroxide of the metal and then hydrogen gas. It's just the ratio of how many hydroxides go with the metal is going to depend on the charge that the metal normally forms. Then we have metals reacting with acids. When it reacts with an acid, it's going to do similar. So the acid, remember, splits up into H plus and then some anion, in this case Cl minus. So the nickel is going to replace what it is similar to. So nickel can form a cation like the hydrogen. So nickel is going to replace out that hydrogen. Now this one can be a little tricky if you weren't given the products, because really nickel could be nickel 2 plus, or it could be nickel 3 plus. Now, which one it actually forms, you have to have more information. But since I gave the products here, you can see that it's forming nickel 2 ion. And so this 2 plus ion is combining with that Cl minus. Okay, but if you were not given any further information and you assumed that it was nickel 3 combining with the chloride, that would be okay as a possible prediction of what products could form. But the basic idea is if you have some ionic compound and it reacts with an element, then it's going to replace the like element in the ionic compound. So metals replace metals, nonmetals replace nonmetals. But then when you have water or HCl, you have to kind of treat those two things as if they were an ionic compound. And so if water were treated like an ionic compound, H plus would be the cation. So a metal would replace the H plus in that. And if HCl or any acid is treated as an ionic compound, again, the H plus portion of that could be replaced by a metal. Okay, so all of your single displacement reactions, it's always something gets kicked out of the compound and replaced by something else. So you should be able to predict products of these things. But even though you can predict a product of a single replacement reaction, it doesn't necessarily mean that that is a reaction that's going to happen on its own. And so it could be something that we have to kind of initiate the reaction. We have to, well, maybe not only initiate, but we have to force it to go. And so any single replacement reaction could occur, but some of them are spontaneous and some of them are non-spontaneous. Okay, spontaneous meaning it happens on its own without energy input, whereas the non-spontaneous are ones that you have to put in energy to get them to work. Okay, and so you can predict these reactions, but if you wanted to know, is this something that would happen on its own? You know, is it spontaneous? Then you would need to use what we call the activity series. Now, here's an example of an activity series. You can find longer ones that have more elements in them. This one is focused on metals, okay? So it shows you what metals are more reactive than others. And it actually also includes hydrogen in here. So that's the only non-metal this particular list includes. But if you were to use this activity series, you can predict whether a reaction is spontaneous or not. And so if you determine it's spontaneous, that's something we would say that yes, this reaction occurs. Whereas a non-spontaneous, we would say it doesn't occur. Well, normally it doesn't occur. We could force it to happen. So this activity series, what it is telling us is that if you have a metal reacting with an ionic compound, that the more active metal is going to replace the metal in an ionic compound. Okay, so if the metal it's being reacted with, if that metal is more active than the metal in the ionic compound, then that reaction will occur. Okay, so anything higher on this list, so it's written with this arrow showing increasing activity, anything higher on the list can replace anything lower. Okay, so if you have potassium reacting with, say, barium chloride, then yes, potassium is higher than barium, so it would replace the barium in the barium chloride. Okay, but if you had the opposite, say you had barium reacting with potassium chloride, well, barium is less active, so it would not replace the potassium in potassium chloride. So we would typically say that there's no reaction, or at least that the predicted reaction is non-spontaneous. Okay, so when you're dealing with metals and ionic compounds, you have to have a metal that's higher on the list or more active in order for the reaction to be spontaneous. Now, if you have a metal and you're reacting it with an acid, then the metals that we would call active metals would react with acids. Okay, and that's everything that is higher in the activity series than hydrogen gas. So we've got hydrogen gas right here. So everything up here above it, all of these are active metals. Okay, so all of those active metals, everything with a higher activity than hydrogen, will react with acids to form hydrogen gas. Okay, and you know, whatever ionic compound results. Okay, so everything above that could react with an acid. But then we have kind of our last kind of reaction of metals, and that's with water. And so when the metals react with water, that's a tougher reaction because water is a really stable compound. And so it doesn't react very easily. So water is only going to react with very active metals. And so the things even higher on the list. So that's where this one tells you a little more. So here we say it reacts with acids to give H2. That includes everything above hydrogen. So not only these 4 that are listed, but the things in green and in yellow. Okay, but then they've got 2 other segments. They've got react with steam to give H2, and then reacts with cold water. Okay, and so those are the very active metals that are going to react with steam or water. So the things much higher on the list. So that grouping in green, those do react with water, but the water has to be very hot, right? It has to be steam, so it has to be in the gas phase, meaning the water is at a lot higher energy state, so it's actually less stable. So it's more likely to react, or it, I guess, gives more energy to the reaction so it can happen. That's a better way to say it. Whereas the stuff at the very top of the list, so above, you know, the magnesium above there, those are things that are very active metals. So even just putting them in cold water, they're going to react. Okay. Whereas the things in green, it's more, they've got to be in extremely hot water to the point where it's steam. And so the activity series is useful in understanding, is this a spontaneous or non-spontaneous single replacement reaction? Because you can always predict what products would form if it happens, but then you utilize the activity series to understand, is it going to happen on its own, or would I need to actually force that reaction because it's non-spontaneous? So let's see. Let's do a couple examples of predicting products for our single replacement reactions. So let's see, this first one I have a metal, so sodium reacting with copper 2 bromide. And so it's helpful if you just think about that standalone element. That standalone element, when it forms an ion, it forms Na plus, okay? And so that ion can replace the like ion. So this is a cation, so it can replace the cation in the ionic compound, meaning it's going to swap out with the copper. So these things are going to swap places, okay? But when it swaps places, that means the sodium ion needs to combine with the bromine as an ion, and bromine as an ion is Br minus. So if I put together the Na plus and the Br minus, then I get sodium bromide, so NaBr, okay? And that ionic compound, since we're in solution, right, because the initial compound's in solution, this is also going to be aqueous. And then I would have the copper now by itself in neutral, so it would just be Cu solid, okay? So the metals are swapping out with one another. Now, the next one, also, I guess we can go back and balance this one. This isn't balanced. We have one sodium on each side, but at the moment we only have one bromine on the right. So I didn't carry over the subscript, and that's because they combine in a ratio to neutralize the charges. Okay, and sodium's only a +1, so you only need one Br minus. So here we're going to need 2 of those NaBrs, meaning we need 2 Nas in this reaction. Okay, now the second one, we've got KCl, so that's our ionic compound, and then we have zinc. And zinc is a metal. The ion that zinc forms is Zn2+. And since that's a metal, that's going to swap out for the metal in the ionic compound, meaning that the K and the Zn are going to swap places, meaning that then that Zn2+ is going to combine with Cl-. So if I have a Zn2+ and a Cl-, then my formula of my ionic compound that forms is ZnCl2, because I need 2 of the Cl- for one Zn2+. And this is all an aqueous solution, so that ionic compound is going to be aqueous. And then we have potassium by itself, so it just becomes K solid. And again, you can go through and balance this. Even though I didn't ask, we're going to balance this. We have 1 zinc on each side, but we only have 1 chlorine on the left, 2 on the right. So I'm going to put a 2 in front of the KCl, which means I need 2 potassiums in the end. Okay, so now it's balanced and I've got my products. Now the last one, I've got fluorine. That's a non-metal. Since that's a non-metal, it swaps out with the non-metal in the ionic compound. And so we think about the ions. When fluorine's an ion, it's F minus, and that's going to combine with the aluminum. So it's going to combine with Al3 plus. When those combine, you need 3 of the F minuses for every 1 Al3 plus. And so that gives me AlF3 is my ionic compound. And since this is an aqueous solution, we'll just assume this is still aqueous, the ionic compound. And then when we have chlorine by itself, that's one of our diatomics. Okay, whereas in these others, when copper and potassium came off, those are metals, so they're just by themselves, okay, and solids. But chlorine's a diatomic and it is a gas. And so that's our products. And then we can balance our reaction. We're going to need 3 F2s and 2 AlF3s, meaning 2 AlCl3s and 3 Cl2s. And so those are our products and our balanced reactions. Let me erase some of this clutter. And if you want to think about how you could use the activity series, that's something that you would use after you've predicted these products, okay? So we predicted the products, we have our balanced reactions, and so this is what would happen if these things react, okay? But some of these things may be non-spontaneous. I don't know. We'd have to look at the activity series. So some of these reactions may happen on their own, meaning we put the stuff together and it just reacts. But some of it we may need to force it if we wanted this to happen. So to figure that out, you could look at the activity series, at least for the first 2. The last one involves a nonmetal, which is not on the activity series I gave. But here, what we would want to look at is we would look at sodium and we would look at copper. Okay, so we're going to go and look at sodium and copper on this activity series. Okay, here we'll erase some of this here too. So I said sodium and copper. We've got sodium and we've got copper. So sodium is higher, meaning sodium's more active. So sodium will naturally just replace copper, okay, spontaneously. So this reaction, yes, is spontaneous because Na is more active than Cu, okay? And then we can look at this next one. We've got potassium and we've got zinc. So let's find those. And so if we look at potassium and zinc, let's see, oh, there's zinc. So potassium's higher up. So potassium is more active. And so if we look at this, well, here, potassium's already in the compound. And so this reaction is showing zinc replace potassium, and that's not spontaneous. So this one's non-spontaneous. Sorry, I'm going to abbreviate this stuff. It's this first reaction. And so this one is non-spontaneous because zinc is less active than potassium. And so that's a non-spontaneous reaction. So the more active thing should end up in the compound if it's spontaneous, okay? So the second one, we would usually say that there's no reaction, but that reaction could happen. It could happen if you force it, okay? So if we put in the energy needed to get that to happen.